Hi, it's Professor Davis. I wanted to take some time to look at ways we can solve exponential equations. So I want to actually just kind of use the rule of three here. I wrote solving these graphically, but I also want to talk about how to solve these kind of equations both numerically and algebraically as well. So let's take a look at the rule we can use for solving equations graphically in general, and this certainly applies to exponential equations. So let's take a look at the rule here. It says let f and g of x represent two functions, function f and a function g. Then the solutions to the equation f of x equals g of x are the x coordinates of the points of intersection. So we could have more than one point of intersection, meaning we could have more than one solution to the equation. So what we want to do is we want to graph an equation and then find its points of intersection. And we can use some numerical means to help us as well. So let's go ahead and take a look at an example here. So we'll begin and solve this algebraically. We'll verify it graphically, and we'll also look at the equation numerically as well. So here it is. It's a general exponential equation. 7 times the quantity 2 minus 10 to the 4x minus 2 power is equal to 8. So think of what we'd want to do here. If we want to solve this algebraically, let's start to take a look at the solution. So there's our given equation in the first line. Now in the second line, notice what we want to do is to divide both sides of the equation by 7. So that kind of removes the parentheses on the left-hand side for us. And then we have a constant there, so we'd want to subtract 2 from both sides. And now, once we get there, notice the coefficient of 10, the base for the left side, is negative. We can simply make that positive by multiplying both sides of the equation by negative 1. So notice here, one other thing before we move on to that, the negative 1 step, is that when we subtract 2, we get 8/7 minus 2. So we need a common denominator. 2 is equal to 14/7, so that's how we get negative 6/7 there. So we multiply by negative 1, and then we have to take the natural log of each side. And the reason being is that the variable is in the exponent. So we'll take the log of each side. So we get the natural log of 10 to the 4x minus 2 power equals the natural log of 6/7. Now, we're not quite done yet. We've got to keep on going. Now, the reason we want to take the log of both sides is to use the power rule. To take that exponent and to take the exponent that was up here and bring it down in front as a coefficient. So we get the quantity 4x minus 2 times natural log of 10 is equal to the natural log of 6/7. And then what we want to do is to divide both sides by the natural log of 10, because that number just represents a constant. So we can just put it down there in the denominator after we divide. And then notice here it's simply a matter of solving this linear equation on the left-hand side. The right-hand side is just this strange looking constant. So we add 2 to both sides, so we have plus 2 over here. And then finally multiply both sides by 1/4. So we get 1/4 times the quantity natural log of 6/7 over natural log of 10 plus 2. Now I took my calculator and approximated that, so let me show you how you can do that too. So let me jump out of here and get my calculator open. So that would be 1/4 times the natural log of 6/7 over the natural log of 10. Close the parentheses on that argument, add 2, close the parentheses there. And so now, notice we get this approximation rounding to 4 decimal places. That would be 0.4833. So that is the solution there to that equation that you saw over here at the bottom of the page. 0.4833. So if now notice here we used about 9 steps to solve that equation. So we'd certainly want to be able to check our work. So that's where our calculator can help us. So we've approximated the solution with our calculator now. Now let's get an idea of what these functions look like. So I took the liberty of entering each side of that equation. The left side I put in y1. So you see the left side of the equation there. y2, I put that constant 8. So notice y2, when we graph that, that would just be a horizontal line passing through the y-intercept 0, 8. The y1, that's an exponential function, and notice since this base here is -10, that function will decrease very rapidly. So let's get an idea of what the graph looks like. I'll hit the zoom key, and then just use the standard viewing window. Option 6, that is. And so notice here you see that exponential equation shoot way down very quickly. It decreases very rapidly. The horizontal line here is at 8. And so it looks like the answer is somewhere between 0 and 1. Alright, and we can tell that by looking at the graph. That's this point of intersection here. Let's just kind of take a look at this numerically now. And to do that, I'll go to the second key and then table set by hitting the window button. Now, let's start our table at 0, and let's use increments. How about 0.05? We'll move kind of slow so we can kind of get an idea of what this looks like numerically. Now, if I hit the second key and table, that's the graph button, notice now we can start to get some idea of what this looks like numerically. Notice the y2 column is constant at 8. So think of what we're looking for a solution here. We're looking for some point where, notice here y1 is greater than y2. We want to keep on going till y1 is less than y2. Notice here at 0.45, y1 is about 9.5 or so, y2 is 8. When we get to 1/2 for x, y1 is 7, y2 is 8. So we can tell by looking at this numerically that the solution is between 0.45 and 5 because the function values of y1 pass through 8, so to speak. So let's go back to our graph now and let's get an idea, a little bit closer picture of this point of intersection that we have up there. So to do that, I'll use the zoom key and then I'll use zoom box, option number 1. We're just going to draw a little box around where we see that point of intersection. So I'll just scroll up here a little bit using the free moving cursor key. Now I want to draw a box around this point of intersection that's right here. So I'll just go ahead and where my cursor is right now, I'll press the enter key and then move up a little bit to get an idea of the height of the box, and then use the right cursor key to open up the box. So now we see we've drawn a box around the solution. Now notice if I hit enter, what will happen is that our entire screen here will be blown up using the dimensions of this box. So I'll go ahead and hit enter. And there we see y1 coming down. There's y2 at 8. So here's our point of intersection right here. So to get the exact point of intersection, we can use the intersect command. So to do that, we'll hit the second key and the trace key to get the calculate menu. So that was second key and trace. And now notice option 5 says intersect. So I'll go ahead and hit number 5. And it asks you which is the first curve. You could have 8 functions in your calculator. It wants to know which 2 curves you want to find the intersection of. Well, it has y1 here. I'll go ahead and pick that by hitting enter. What's the second curve? Yeah, that's y2. I'll go ahead and hit enter one more time. And then it says take a guess. Well, I don't need that great of a guess. I can kind of be, maybe over here. It doesn't matter that much. Now I'll go ahead and hit enter one last time. And notice there's our point of intersection. The x-coordinate is 0.4833, rounding to 4 decimal places, and if you recall, that's exactly the solution that we got algebraically, and we also squeeze that together numerically too. So that's how we can solve exponential equations 3 ways using the rule of 3: algebraically, numerically, and graphically.